Hey guys, IBM is here with part 3 of Feb March paper 4. This is Physics 9702 paper 4 Feb March series. So this is going to be part 3, and I want part 3 to be questions 5 and 6. So a capacitor of capacitance C1 is connected in series with a second capacitor of capacitance C2. Show that the combined capacitance C of the two capacitors is given by that expression. So in series, the charge is the same. So because it is in series, we shall say charge is the same. Charge is the same. So the charge for capacitor 1 can be Q1. Let's say the charge for capacitor Q is Q2. And the total charge is Q. So the charge is the same and is the same as the total charge. So it means Q equals to Q1, which is the same as Q2. That is 1 mark. So that means the PD is going to be shared. If you look at the capacitors being in series, so the total PD is V. If this is C1 and this is C2, this is going to be V1 and this is V2. The charge on each of the capacitor plates is the same. So total PdV is the same as V1 plus V2. So that is the second mark. The other algebra is just emphasizing this. And of course, we know that capacitance is related to the PD by the equation V equals to charge over capacitance, or capacitance is charge over potential difference. So it means when I substitute here, this means that V1 is going to be Q1, which is just Q over C1, and V2 is going to be Q over C2 because Q1 and Q2 are the same as Q. So it means we substitute in this equation, we shall have that Q over C equals to Q1 or Q over C1 plus Q over C2. This is just Q. So when you do the algebra, this implies that Q over C is equal to Q into 1 over C1 plus 1 over C2, which implies that 1 over C equals to 1 over C1 plus 1 over C2 because the charge cancels. 3 identical capacitors, each of capacitance C, are connected in a network as shown in the figure here. So we have 2 capacitors in series and their combination is in parallel with the other one. So for capacitors in series, their total capacitance is obtained from the reciprocals, and for capacitors in parallel, their total capacitance is obtained by summing up. The variation of the charge Q with the potential difference V between the terminals X and Y are shown here. So Q against V is indicated here. Show that C is equal to 45 microfarads, so that the capacitance of just one capacitor is 44 microfarads. Okay, so total capacitance in series. Total capacitance in series. We have seen here that in the series total capacitance is 1 over C1 plus 1 over C2, which is the same as C equals to product, which is C1, C2, over the sum, which is C1 plus C2. When you get the LCM, get the reciprocal, this is what you get. So for capacitors in series, total capacitance is the product over the sum. So total capacitance in series, I'll call it total capacitance in series is going to be C times C over C plus C, which is going to be C squared over 2C, which is the same as C over 2, or it is just half the capacitance of 1. If you know that, you don't even need to derive that. Then for capacitance in parallel, we sum up. So it means total capacitance, total capacitance, I'll quote C total, is going to be the capacitor which is in series, which is in parallel. This one is in parallel with the C over 2, so we sum them up. So this is going to be C plus C over 2. LCM is 2, so we have 3C divided by 2. And from this graph here, of course, we know that the gradient, since we know that capacitance is charge over V, which is going to be equal to the gradient, or you can just take values from the graph and substitute because the line goes to the origin. So we shall also say that total capacitance is going to be equal to the gradient, which equals to, I'll just take the extreme values. This is 6 volts and this is 400 microfarads minus 0 minus 0. So this is going to be 400 times 10 to the power of minus 6 divided by 6.0. So I'll just simply say that 3C over 2 is the same as 400 times 10 to the power of minus 6 divided by 6. Or you could say C equals to 2 times 400 times 10 to the power of minus 6 divided by 3 times 6. From my calculator, 2 times 400 exponent minus 6 divided by 18. So that is 0.00044 recurring, or which is 4.4444 times 10 to the power of 1, 2, 3, 4, 5 minus 5. So this is 4.44 recurring times 10 to the power of minus 5 farads, which is, when I change to micro, you divide by 10 to the power of minus 6. So 4.44 10 to the power of minus 5 divided by 10 to the power of minus 6 to have microfarads, which is 44.4 microfarads, or it is approximately 44 microfarads. The capacitor network in the figure 5.1 is charged and then connected to a resistor of resistance 54 kilo ohms. The capacitor network discharges through the resistor. The time constant, remember the time constant is the product of R times C, that is resistance times the capacitance. Give a unit with your answer. Of course, the unit for time constant is the second. We showed why the unit, you might have seen why the unit is the second. If you haven't, you can watch videos of alternating, capacitance as a unit as under the lessons. Just look for lessons of capacitance under the playlists. So the time constant tau is equal to R times C, and of course the C is going to be the total capacitance C. They say the capacitor network in the figure is charged and then connected to a resistor. So it means we are considering total capacitance here. So this is going to be the resistance is 54 times 10 to the power of 54 times 10 to the power of 3. Then total capacitance is 3 over 2 times the capacitance of just 1, which is 44 times 10 to the power of minus 6. This is the total capacitance. And when you press your calculator, so you have 54 exponent 3 times 3 times 44 exponent minus 6 divided by 2. So this is giving us 3.56, or approximately 3.6 seconds. So the time constant is 3.6 and the units is seconds. Determine the time taken for the discharge current to reduce to 15%. So we want the discharge current to reduce to 15 point. So the current equals to I naught e power negative t over the time constant, and we want I to be reduced to 15%. So I is going to be 15% of I naught, which is 0.15 of I naught. So we have that 0.15 I naught is equal to I naught e to the power of negative t over the time constant, which is 3.56 or 3.6. So introducing natural logarithm, of course, I naught cancels out. So we have that ln of 0.15 is going to be equal to the power. Of course, when you get ln of e to the power of that, you only remain with the power. So that is equal to negative t divided by 3.56. So alternatively, you could have that t is equal to negative 3.56 ln of 0.15. So negative 3.56 ln of 0.15, that is 6.75 seconds, or approximately 6.8 seconds. Okay, so that is question 5. Question 6. An electric field and a magnetic field are used to form a velocity selector. Of course, a velocity selector is made up of a crossed field. Charged particles called ions pass into a region of uniform electric field and magnetic fields that is between parallel plates as shown in the figure. Okay, so the electric field is downwards because it's always from high potential to low potential. Region of electric and magnetic fields. The potential difference between the plates of the velocity selector is V. The separation of the plates is D, and the magnetic flux density is B. Show that the speed u of ions that pass undeviated through the velocity selector is given by the u equals to v over b times d. Okay, so we have already seen that the electric force due to the electric field is downwards. If the ions are to be undeviated, it means that the force due to the magnetic field must be upwards. When I write FB, that is the force due to the magnetic field. And when I write Fe, that is the force to the electric field, must be downwards if the ions are to go through undeviated. And then also the force to the electric field must be equal to the force to the magnetic field. Other than being in opposite directions, they should also be equal in magnitude. So the electric force, let me just write a word, electric force equals to charge times the electric field strength, which is the same as charge times V over D, because electric field strength is also V over D. Then the magnetic force, of course the magnetic force is given by BQ. Because the speed of the ions is U, I'll just use BQV instead of V, I'll use U. But we normally use V for speed, so it is BQ times U. So the electric force, for no deviation, the electric force is equal to the magnetic force. So for no deviation, so the electric force should be equal to the magnetic force, which means that BQ times U should be equal to QV over D. And the Q cancels out. So Q cancels out. Let me use a different color for cancelling out. Which means that U is equal to V divided by D times B, which is the same as V over B times D as required. Positive ions with kinetic energy 4.1 times 10 to the power of minus 17 joules and mass 3.2 times 10 to the power of minus 27 kilograms pass undeviated through the velocity selector when V is equal to 980 volts and D is equal to 3.6 exponent minus 2 meters. Determine B. So because they've given us kinetic energy, we know that kinetic energy equals to a half times the mass times the speed squared, so that is times U squared. And this means that U is going to be equal to twice the kinetic energy divided by the mass under the square root. And remember, U is also equal to V over B times D. So we want to find B. Therefore, it means that B is going to be equal to, I'm cross multiplying, so it is going to be V divided by D times the square root of twice EK divided by M. So B is going to be equal to V, the potential difference, V is 980 volts, divided by D, which is 3.6 times 10 to the power of minus 2, then times the square root of 2 times the kinetic energy, which is 4.1, times 10 to the power of minus 17. This is divided by mass, which is 3.2 times 10 to the power of minus 27. Okay, I'll press my calculator. I will start with the root. So with the root, I have 2 times 4.1 exponent minus 17 divided by 3.2 exponent minus 27 under the square root, then times 3.6 exponent 3.6 exponent minus 2. So I have 980 divided by this answer. So I'm getting 0.17. So this is 0.17 Teslas. A proton passes undeviated through the velocity selector. It is a proton which is positive. So it passes undeviated through the velocity selector. First of all, for a positively charged particle, if the particle is positive, the force to the electric field is in the same direction as the electric field. So the electric force is going to be downwards on the positively charged particle, and then it means that the magnetic force must be upwards on the positively charged particle. So we now know the direction of the magnetic force, we know the direction of the particle. So using Fleming's left-hand rule, if you try to employ Fleming's left-hand rule, you can also watch magnetic fields, where I've used Fleming's left-hand rule many times. There's a playlist labeled magnetic fields, which is past paper questions. You'll see the left hand there demonstrated clearly with the images of the left hand. So if we use Fleming's left hand rule, it means the first finger pointing, the second finger pointing in the direction of the positively charged particle. That is the first finger, that is the second finger. Because the second finger points in the direction of the current, which is the same direction as the flow of positive ions, and the proton is positive, the thumb must be made to point upwards. If you try this on your table, if the paper is on the table, and you make the first finger point to the right hand side, and the thumb pointing towards the top of the page, the first finger must be pointing onto the page, which is on the table. That means the electromagnetic field must be into the page in this case. But let's see what the question wants. An alpha particle enters the velocity selector at the same speed, so v is the same as u. State how the expression in A predicts that the alpha particle also passes undeviated through the velocity selector. So I want you to note that for no deviation, okay, we want to use the expression in A. The expression in A is telling us that u equals to v over bd. You notice that there is no speed in this expression here. So if there is no, of course, for an alpha particle, its mass is 4u, or 4 times 1.6 times 10 to the power of minus, so 1.66 times 10 to the power of minus 27 kilograms. Its charge is 2e, which is 2 times 1.6 times 10 to the power of minus 19 coulombs. So we notice there's a difference between an alpha particle and a proton, but in this expression here, there is no charge, there is no mass. So it's independent of the charge or the mass, as long as the speed v is the same as u. So we shall say the expression is independent of mass and charge. The expression is independent of mass and charge. The only difference between a proton and an alpha particle is their mass and the charge. Since the speed u is the same, u and v are the new speed v are the same, and there is no charge and mass in this expression, then again the alpha particle will be undeviated. By reference to the figure 6.1, this one here, and to the forces acting on the positive ion, determine the direction of the magnetic field. We want to determine the direction of the magnetic field, and I think I've tried to explain that earlier on. They said, explain your reasoning. Okay. So I'm going to try and explain my reasoning here. I will first sketch. So this is a magnetic field, an electric field. This is positive, this is negative. So if a positively charged particle is entering, there, this is in the direction of its speed. So when the particle enters, we have already said that the electric force on a positively charged particle is in the same direction as that of the electric field. The field is downwards. So the electric field is downwards. So the electric force is also in the same direction as the electric field on a positively charged particle when it enters the electric field. But for no deviation, we must introduce a magnetic field which causes a force in the opposite direction. So the magnetic force must act in the opposite direction for no deviation. And of course, for no deviation, the two forces are equal. So by Fleming's left hand rule, I said make the first finger to point to the direction of the positively charged ions, and make the second finger, this is second finger, and make the thumb to point towards the top of the page. So this is the thumb. And if you do that, you notice that the first finger will be pointing into the page. The first finger points into the page. If you want more explanation, visit or check out magnetic fields under the playlists. The solved past paper questions for magnetic fields. There's a free document in the video, in the links, the video links on the video description for you to practice magnetic fields and using Fleming's left-hand rule. So it means we shall say that the electric force is downwards because I said the electric force on a positively charged particle is always in the same direction as the electric field. So electric force is downwards. Electric force is downwards, so the magnetic force must be upwards. So magnetic force must be upwards. Must be upwards since there is no resultant force. So the magnetic force must be upwards since there is no resultant force. Okay? Since the particle is positive, the current is from left to right, or the second finger points from left to right. So since the particle is positive, the current is from left to right. The current is from left to right, of course, perpendicular to the magnetic field. Thus, by Fleming's left Fleming's left-hand rule, the magnetic field is into the plane of the page. Okay. Positive ions in B enter the velocity selector with a greater kinetic energy. On the figure, sketch the path of the ions. So they are saying these ones enter the velocity selector with a greater kinetic energy. And of course, we know that kinetic energy is directly proportional to the speed squared. So greater kinetic energy implies that the new speed or speed of positive ions is greater than u. So the new speed is greater than u. What does that imply? Remember, for no deviation, we know that Fe, or the electric force, is supposed to be equal to the magnetic force. The electric force is given by Q times E. The magnetic force is given by B, Q times U. So this means that U equals to E over B, or a greater speed means that the new speed is greater. So this means this part is going to be greater. When the new speed is greater, it means that this part is greater, which means that the magnetic force is now greater than the electric force, because the electric force is not changing. So for greater speed, it means the magnetic force is going to be greater than the electric force, because the magnetic force depends also on this speed. So a greater force means a greater speed means a greater magnetic force. Therefore, the particle must be deviated in the direction of the magnetic force. So deviation is in direction of the magnetic force. Remember, we said the magnetic force was upwards since the electric force was downwards. So the deviation is going to be towards the top. So I'll go to the diagram. I'm going to remove all these ones because they were not necessary. So the particle is going to be deviated towards the top. Of course, if this was in a vacuum, of course, when you come out of the field, you put a ruler and draw a tangent. This part here should be a straight line. This part here should be a straight line, but make sure it is a tangent to the curve. It is a tangent to this curve. So this is the path. The path is going to be towards the upper part, but remember, or towards the top plate, because the magnetic force was upwards. But I want to encourage that outside the field, make sure you put a ruler and draw a tangent to the curve to make this part to be a very perfect straight line. I don't know if I can try that. It's really very hard to sketch this. Okay, so you can try to do a very perfect smooth curve. A very perfect smooth curve, and when it emerges, you put the ruler to draw a perfect straight line. Okay, so I think that is part 3. See you in part 4. Bye bye. But don't forget that this should be a continuation of this. Mine is not very perfect because I'm drawing on a computer and I'm using an electric pen, which makes it even harder to sketch. But it's a smooth curve, and the line should not be bent, it should be a perfect tangent to the curve. Until next time, bye bye.